Hi everyone and welcome to this video about logarithms. Before we begin the content of this video, please remember to like and subscribe if you enjoy it. Remember, you can ask any question you want about this video down in the comment section below, and if you would like me to make a video on another topic, please comment that down below as well. We know that exponential functions exist in the form of a constant raised to a power of x, or another unknown variable, and we've probably also come across Euler's number e. Logarithms exist as an inverse of an exponential function. For example, if we have y equals 2 to the power of x, in order to rearrange this equation to have x the subject, we're going to need to do the inverse function of what is happening on the right-hand side. We have 2 at the base of this right-hand side, and we have the power being x. The inverse of what is being done to x is log to the base of 2. So what happens would look like this. I would apply log to the base 2 of both sides of this equation. As I said before, log to the base 2 is the inverse function of having 2 at the base of an exponent. So on the right-hand side, log 2 and the 2 at the base of the exponent cancel out, leaving me with log to the base 2 of y is equal to x. I can also demonstrate that log to the base 2 is the inverse operation of having 2 at the base of the exponent by writing an expression like this. 2 to the power of log to the base 2 of x is also just x. So applying one of these functions after the other has the effect of cancelling the previous one out. Let's express this in a general case. Log to the base of a constant a of another number n is equal to x. This means that n is equal to a to the power of x. It's important to note that the base of a logarithm cannot be 1. Let's look at this example where we're going to rewrite some expressions in terms of logarithms. So for this first question, we can see that the base of this exponent that's happening on the left-hand side is 3. So we know that applying log to the base 3 of both sides will remove that 3 and leave us with the 2. So we can see that log to the base 3 of 9 is just 2. For the central question, we can see that the base of the exponent is 2, so we apply log to the base 2 of both sides, leaving us with 7 on the left and log to the base 2 of 128 on the right. For part C, we see that the base number is 64, so after applying log to the base 64 on both sides, we get a half on the left-hand side. We're asked to rewrite the following with a power or an exponent instead of a logarithm. The base number of the log in part A is 3. So taking that number and placing it on the base of both sides will remove the log on the left. So 3 to the power of log to the base 3 of 81 equals 3 to the power of 4. On the left-hand side, we would have 81 remaining, and on the right-hand side, we'd be left with 3 to the power of 4. And of course, 3 to the power of 4 is indeed 81. For question B, we can see that logarithms are capable of processing fractions. Here, the base of our logarithm is 2. We can take both sides of our equation, place the number 2 as the base. On the left-hand side, log to the base 2, and having this 2 at the bottom of our exponential will leave us with just 1 over 8. And indeed, 2 to the power of minus 3 is 1 over 8. Looking at our third example, we can see here log to the base 3 of 81. Now in your calculator, you will have a button that has log, and then a square for the base, and another square for the input of your logarithm function. So you could just place part A into a calculator in order to work out the answer. But we can actually work this out without using a calculator. Let's set this equal to x. Now with log to the base 3 on the left, the inverse of this operation will be having 3 as the base of the exponent. So 81 equals 3 to the power of x. I can now just consider what power do I need to raise 3 to in order to be 81, and x, of course, is 4. You can try doing this with this button on your calculator, and you'll see that we work out the same answer. As for the next question, we can again set this equal to x, taking the base of my exponent to be a, and I can see that if the two sides are to be equal, we need to have x equals 5. Let's return for a second to Euler's number e. Let's say we have this equation set up for us. Well, in order to solve this, we know that the inverse operation of an exponential is a logarithm. In this case, the base number is e. So on both sides, I would apply log to the base e. I can see on the left, log to the base e and the e would cancel, leaving me with x equals log to the base e of 5. Log to the base e looks a little bit strange, and we don't normally write it like this. We would write it like this ln, pronounced ln, and on your calculator you should be able to find this button here. We could rewrite this final expression as x equals ln 5. So to summarize, log to the base e is ln. You might also see log to the base 10 being shortened to just log, or lg. Let's do a quick final example. We have log to the base 2, so we know in order to remove the logarithm, we need to take both sides and place them as the powers to the base 2. We can see that on the left we would have x minus 1 remaining, and on the right 2 to the power of 3 equals 8. So here my final solution would be x equals 9. Thank you for watching this video. I'm glad you've made it all the way to the end. If you have any questions about the video, remember you can leave them down in the comments section below. Please like and subscribe if you enjoyed it, and I will see you in the next video.